Hello, this video is section 4.1 from the Larson book, the probability distribution for a discrete variable. Now the first definition we're going to look at, a random variable. It must represent a numerical value associated with each outcome of a probability experiment. So they can't be categorical word responses, they have to be numerical. And there's two primary types of discrete and continuous random. They're discrete and continuous. And let's define what each of those are. All right. Discrete is a finite or countable number of possible outcomes. Now, anything that if it starts out the number of something, for sure it'll be discrete. But it can be, discrete that anything where it only takes, and we'll see some, monetary type of problems later where, let's say, you're investing in something or gambling or whatever, you could either lose $10 or win $20. That would be discrete. They wouldn't be countable, but it would only be specific outcomes, not a range of values. And that's what continuous is. Continuous is an infinite number of outcomes that you could represent on an interval on a number line. Measurements like time, height, volume, temp, even if whatever the display showing you the measurement is, even if it shows it only in whole numbers, it doesn't mean that it can't take on values in those intervals. See, there's always I'll just put an example of an interval here. So say we got 2 to 6. In algebra and interval notation, that means any possible real number between 2 and 6. So, 3.5792, something like that. One more quick example I'll give you. If any of those are going to be just continuous, I usually have one question on a test where it gives you a variable. We're going to look at some examples and then ask you whether it's discrete or continuous. So let's say you've got a 16-ounce bottle of something to drink, water, soda, whatever. Well, technically, especially if you have the more sophisticated measuring devices, but even then, the amount of volume in that bottle can be anywhere from 0 to 16, any real number. I mean, theoretically, it could have 11.537 ounces in it if you had the ability to measure it to that fine of a detail. But it's not just whole number of amounts. In other words, it's not either, well, you've got 0 or you've got 1 ounce or you've got 2 or you've got 3. That's not right. Anything between 0 and 16 would be possible. So let's look at a few of these. Look at some of these. So number of goals scored in a soccer game, that would be discrete. Like I said, the number of anything is discrete. Number of home runs in a baseball game is discrete. And you don't have to even know how many there are going to be. In other words, before a baseball game even starts, it could be, you don't have to have a stopping point, in other words, but it's going to be either 0 or 1 or 2 or 3 or whatever. It's not going to be 1.57 home runs hit in a game. The time it takes to complete a baseball game, that would be continuous. Time is going to be continuous. The number of defects found on an automobile final inspection, that's discrete, because if you're just counting the number of defects, it's going to be countable numbers. The temperature of a pizza oven at a particular time, and once again, ignoring, displays are only going to show you, whole number temperatures. But obviously, temperature does not have to be a whole number. It could be in intervals between whole numbers. The amount won or lost based on a $5 even money roulette bet, you're either going to lose 5 or you're going to win 5. So that would actually be discrete. It's not countable, but means it only has those two outcomes. And I've already talked about this one, the liquid in the bottle, but that would be continuous. And the number of questions answered correctly on a multiple choice exam with 20 questions, that would be discrete. It's perfectly countable. Let's talk about a discrete probability distribution. A discrete distribution with random variable x. Sometimes you might see things where they throw in other, like z or something like that, but it's It doesn't have to be X, but I think it's good form if we use X. But don't panic if you saw a chart that had Z there or something. So discrete probability distribution, what it is, it lists all the possible values of X, and then you write right below it or beside it if it's vertical. Sometimes these are vertically or horizontal. I do them usually in the notes horizontal. When we look at my stat lab problems, you may see them vertically. I just do them horizontally just to kind of save space on the page. So either you write the probability either below the X or next to the X if it's vertical, and you'll see that. So let's look at one example here. Let's say X has to be numerical, so we roll a single die and let X be the number of dots facing up. So you see here I've listed the values of X would be, all possible values of X would be 1, 2, 3, 4, 5, and 6. And then the probability of each individual number would be 1 out of 6. So each of these probabilities would be 1 out of 6. Now, don't make the assumption that every time you do a distribution, the probabilities are all going to be the same. That's not true, but it is in this example. Anyway, now any valid discrete probability distribution must satisfy the following two conditions. Now, number 2 will be something we haven't looked at until now, but we've definitely talked about the first one in chapter 3. The probability of any value has to be between 0 and 1. So we already know that. But now, this one says the sum of your probabilities in your distribution must add up to exactly 1. Meaning you've got 100% chance that one of those is going to occur. Like this one would be rolling a 1 or 2 or 3 or 4 or 5 or 6. So they have to add up to 1. So no, adding up to 1 doesn't mean it's right, but if they don't add up to 1, then you know it's wrong. Now let's look and see if these distributions, if we think they might be valid by that definition. Now the values of X do not matter. That's not important. So you say don't let that negative X. Yeah, those X's can be anything. We're just looking at the probabilities. So we have 4 probabilities. Individually, they're all fine. They're all between 0 and 1. That part's good. But when you add them up, which I did here in the calculator, they add up to 1.1, which is not equal to 1. Therefore, that probability distribution is not valid, not possible. The next one, each individual probability looks good. They add up to 1 exactly, so that's a valid distribution. Now the next one, we have a negative probability in there, so that's it. That makes it not valid. On purpose, though, I did make them add up to 1 just in case. I made them add up to exactly 1, which so it satisfied that part of the process. But no, it can't have a negative probability, so that one's not valid. All right, so that's not too bad. Now this one's not too bad either. All right, so if you have one missing value, in this case, like right there, and you know the other values, could you figure out what that value would be? Absolutely, because we know they have to add up to 1. So all you have to do is take 1 minus the sum of the other 3. Now I just put it in parentheses right here. You can add them up first if you want to, and then just go 1 minus that number. Whatever you do, then do it correctly. You'll end up with 0.16. Obviously, you can double check that and then add 4 of them and see that add all 4 of them and see if it adds up to 1. All right. Now let's take a look at these questions. I like to put at least one of these on a test, maybe 2, but maybe only 1. So here's our distribution. I want to just show you. If given a question like this, and if they're not asking if it's valid or not, unless it's a mistake, but that shouldn't be the case. It should be valid, but I just made a note of it over here that it was. So anytime they give you one, it shouldn't. It's not. The idea is not to trick you and give you an invalid distribution. So we want to solve these probabilities based on these distributions. So now you got to be real careful with reading your inequality symbols from algebra. It's got the bar below it. That means equal. So this is saying x between 1 and 3, And if you got to equal at both of those, that means you include 3 and you include 1. So all the x's between 1 and 3 would be 1, 2, 3. So the probability would be these 3 probabilities added together. And we get 0.61. Now the next one has an equal at 1, but it does not at 3. So that means we include 1, but we don't include 3, so it's just 1 plus 2. So we add these two numbers together and get 0.29. Now the next one is between 1 and 4 and doesn't have an equal at either end, so we don't include 1 and we don't include 4, so that would just leave 2 and 3. So we add up the probabilities for 2 and 3 and get 0.40. Less than or equal to 3. That's different than less than or 3. Less than 3. Less than or equal to 3. We include 3, 2, 1. All of those. We add those 3 up. And we get 0.61. The next one's greater than 3. Obviously, that's different than greater than or equal to 3, which would include the 3. But strictly greater than 3 would only be the 4 and the 5. So we add those 2 up. And greater than 5. There are no x's greater than 5. That would be 0. Less than 6. They're all less than 6. Add them all up. That probability will be 1. All right. Let's flip a coin twice here. You could use a tree to get these values if you need to, or with 2 coins, you probably could just list them out easily enough. But the possibilities are head, then head, head, tail, tail, head, tail, tail. So you may be thinking, hey, thinking towards me, didn't you tell me that that x has to be a numerical? The random variable has to be numerical. That's correct. These are not numerical. So x has to be defined from this experiment in a way that would make it numerical. And here's what we came up with this one. You could do tails or heads. So let x be the random variable that counts the number of tails that appears in both tosses. So you now see, even though we're dealing with heads and tails, we're going to have a numerical outcome. And before I scroll down, let's see what that's going to be. Okay. If we flip a coin twice and we're counting how many tails, we can get no tails, 0. If we do it and count number of tails, it's possible to get 1 tail. And then it's possible to get 2 tails. So the only possible outcomes here are 0, 1, and 2. If you flip a coin twice, or both at the same time, and you're counting the number of tails, the only answers you can get are 0, 1, and 2. There's no other answer you can possibly get. You would have to flip the coin, more times to get more answers. So we know these are the x's here, 0, 1, and 2. Okay. Now, let's get the probabilities. So you go back up here to the sample space and you see there are four outcomes here. Now, the number of outcomes that represent 0 tails would be the heads right here, the first one. So you got a 1 out of 4 chance of that happening. The probability of getting exactly 1 tail, well, there's 2 ways you can do that. It could be head then tail, tail then head. So you got a 2 out of 4 chance of that. And the last one, the probability of getting exactly 2 tails would be 1 out of 4. So you see that each probability is fine, then they add up to exactly 1, which is good. But like I was saying earlier, adding up to 1 doesn't mean it's right. Because for example, if you just wrote down there 1/3, 1/3, 1/3, that would add up to 1, but it wouldn't be correct. But the important thing is not adding up to 1 means we have a mistake for sure. So, for example, let's say if you would have wrote 1/4, 2/4, 2/4, and then you double check and go, hey, that adds up to 5/4, so I know something's not right here, and then you could fix it. Excellent. Now, let's say we're going to take some ping pong balls and maybe get a Sharpie and write some numbers on them, 1, 2, or 3, and let's say we write them down in this fashion. decide I wrote 2 1s, 3 2s, and 5 3s. Now I wrote the frequency distribution over here just to show you. We don't really need that. This will be the actual probability distribution. So, which is the frequency distribution, relative frequency, but then divided by the total to make it relative frequency, which is our probability. So essentially, you got 10 balls. So you pull one out, and what's the probability you get each of these? Well, there's 2 1s, so you got a 2 out of 10 chance of getting a 1. For the 2s, 3 out of 10 chance. For the 3s, 5 out of 10 chance. And my probabilities do add up to 1, so that's good. Now let's talk about the mean of a discrete distribution, the average. It's pretty easy to calculate. And this, basically, it's the average of the variables. They're kind of like a weighted mean, you know, we've talked about before, sort of like that. It is a weighted mean. But anyway, but it also represents, it would represent the theoretical average. Like if you repeated this experiment over, you know, according to the law of large numbers, over and over and over and over, and we were recording each number we got, whether it was a 1, 2, or 3, you would expect the average to be somewhere near that particular value. So here's what you do. It's not too bad. You just take each x and multiply it by its respective probability. And then you move over. So you go like this: x times p for the first one, move over, x times p, move over, x times p, and then you add those up. So here, come down here, and we'll see how this example goes. And we have 1 times 2 over 10, plus 2 times 3 over 10, plus 3 times 5 over 10. And the average would be 2.3. The mean would be 2.3. Now this book doesn't necessarily use this term EMV, a more expected value is a more accurate term. I'm going to leave that EM. That's not going to really cause you any grief, I don't think. So that term is from another book, but it's the mean. But when we talk about this EMV, or more specifically EV, I'm almost tempted to change these to EV because expected value is kind of what we're usually used to using. Let's see. So I may just say EV even though it says EMV. But this is when you kind of have monetary outcomes involved in the problem. Money loss. And our random variable x is going to be the net gain or loss per a certain situation. Okay. Now this example says we have a short-term business venture. That has a probability of 1 over 10 of profiting 12,000, a probability of 4 over 10 that we break even, and a probability of 5 out of 10 of losing 3,000. What is the expected value of this adventure? So there's 3 outcomes. Break even means, 0. We're looking at it as profit loss 12,000. We win 12,000. Break even 0. Now here's where you got to be careful. If you remember this, then you'll have no trouble if you don't make this mistake. Even though you don't see a negative sign in the problem, there's no negative on the number, losing $3,000 makes it negative. So the word losing makes that a negative 3,000. So if you're careful there, you're great. So we got 1 out of 10 for the probability of winning 12,000, 4 out of 10 break even, 5 out of 10 of losing 3,000. So you just do the calculation, x times p, x times p, x times p. And that comes out to be negative 300. Okay, now, so what that basically means is, because you're not going to lose, negative 300 on any one outcome, but that means that if you did this experiment over and over and over, and that's what I'm editing right here, I'm making it a little smaller, you should, on average, you'll lose $300 each on average, and that's no good. If you do it a lot of times, that's going to be a lot of money, so that's not really a good business venture there for us. I mean, yeah, you could get lucky the one time and quit, first time and quit maybe, but Yeah, this came from another book here. It's kind of interesting because it's, there's no real definition here of what no oil, some oil, much oil means, but that doesn't affect the problem, so it's not that big a deal. So some oil drilling experiment, minus 40,000. If we lose 40,000, if it was no oil, we got a 0.25 probability of that happening. Whatever some oil means, we'll profit 10,000. We have a 70% chance of that happening. And much oil will profit 70,000 with a 0.05 probability of doing that. And I'm just making note here that the probabilities do add up to 1. And then we just do the XP. So these first two, next two, add them up, and we get positive 500. So that means, in theory, we should average $500 profit per attempt. All right. Okay, roulette wheel. Roulette wheel has 38 equally spaced numbers. Well, there are some wheels with 39 numbers, but we're not getting into that in our class. This is fine. 8 and 37 even is also 18 red, 18 black, and 2 green. And let's say so. Obviously, you needed with this breakdown right here is sufficient enough for you to figure out these probabilities. Now, you don't have to have a knowledge of gambling here or whatever, but we're going to walk up, we're going to bet $5 on black. And what's going to happen here, it's called an even money bet, because that means you're either going to lose $5 or you're going to win $5. Or if you have a $5 chip out there, they're going to add another $5 chip out there. That doesn't mean you won $10. It means there's $10 in front of you, but you only, you gained $5. So there's two outcomes. Lose 5 or win 5. Negative 5, positive 5. So we lose 5. We're betting on black. So there's 38 numbers total. We got 18 blacks working for us. We have 18 red and 2 green working against us. So it's 20 over 38 working against us. Then the black, 18 out of 38 working for us. You see I just made a note here that the probabilities do add up to 1. Yeah, that would be in case you accidentally wrote 18 over 38 and 18 over 38 and forgot about the greens. And then you would add it up and go, hey, that's 36 over 38. No good. So to calculate this, not too difficult. Negative 5 times 20 over 38 plus 5 times 18 over 38. Negative 0.263. So what that means is that on average, you would lose about 26 cents on average per bet on a $5 bet. So that's the casino's looking at it. So you don't want to become a professional roulette player, but if you're just, at a casino gambling, having fun, bringing cocktails to you and whatnot, I'm not saying don't play it, just don't play it as a profession because you're going to lose. So they're taking 26 cents on average every $5. So the house, the casino is looking at it from all players, not looking at you specifically. They're looking at how much are they bringing in, and to convert this to a percentage, which I would never ask you to do this, but if you take that number and divide it by 5, that gives you the advantage that they have a 5.26% mathematical advantage on the game roulette. They don't have to do anything to try to cheat the game or anything like that. The long-term mathematical expected value will work in their advantage. Wonderful. All right, so here's one that says car wash loses $30 on a rainy day. So you see loses is negative 30, makes 120 on days, makes profits 120 when it doesn't rain, plus 120. If the probability of rain is 0.15, calculate the car wash's expected profit. Now notice it only gives us one probability here. It didn't give us both probabilities. That's the key here, is that if there's only two outcomes, it only has to give us one. It could give us both. Like if there were 3 or more outcomes, you couldn't get by with just one of these. But remember the idea of a complement that we've learned before. If the probability of rain is 0.15, then the probability of not rain is 1 minus 0.15. So you see they didn't give us that number, but it was super easy to come up with. So then once you have that, you can do the calculation. Negative 30 times 0.15, 120 times 0.85, and we have 97.50. So they should average profit of 97.50 per day. All right, let's look at, all right, I'm going to skip through some of this because you're not going to have to use these formulas. Well, we sort of have to in Excel. This one, right? We'll be using this one if you want to use Excel. If you use the calculator, you don't have to worry about the formula. But I might just show you one real quick. The variance, of course, standard deviation is always square root of the variance, always. No matter what kind of variance formula you are given, the standard deviation will absolutely be the square root of that. And this is only population. There's no sample here, because when you do a probability distribution, that is the distribution of the population of all the x's. There is no sample. In fact, when I show you in the calculator, you know, back what we did before, it always showed you an SX and a sigma x. It showed you both. Here, it won't even show you the SX. So what this says is, you know, you get the mean from right here. We've already seen that. You take the x times p of x, you add those up, and then you create a square of the x's, an x squared, multiply that times the probability, add those up, then subtract whatever this number is squared. So like I said, you're not going to have to, but let me just show you kind of quickly how it works on this one. So this here was a distribution. In fact, I have this in Excel. Okay, now we'll do this in Excel for a new example here in a little bit, but I can explain what's going on right here in the meantime for this one. And the same thing with calculator. I'll show you new examples there. Let's see what we got here. So, okay, XP, XP, XP. I went ahead and create an X squared row here because I'm going to need that in the next step. So XP, 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 8.4, there's your mean, 8.4. I like this formula, top formula, better, and that's the way I did it in Excel too. So now I'm creating an X squared P thing here. So you see the X squared P's are next to each other. 4 times 0.12, 25 times 0.28, so forth, so on. You add those up, but that's not the answer for the variance. You do add those up, but you see right here, though, at the end, you subtract the square of that mean. So you subtract 8.4 squared at the mean. Back in the old days, when people were using technology more and whatever, and well, they were using calculators, but they were doing the formula, they would often forget to subtract this part right here and just add those up. So your variance is 18.12, and your standard deviation is the square root of that, so it's rounded to 4.26. So like I say, you're going to watch me work through this in a little bit. So it's basically, you get your data in there, you want your x's in L1, and you want your p's in L2. And now, though, this is a little bit different. When we were doing these calculations in the earlier chapters, you know, we only had one column of data. So we weren't using this space right here, right below the list, right there where it says frequency list. We didn't have anything there. That was blank. Now, though, you have to put L2 in there, and I'll show you how to do that, but you just basically go L2 is this blue one right here above 2. You go alpha L2 like that. So you need this here, but then one thing to keep in mind if you're going back, you know, to do statistics on one sample data again, and you want to perform the one var stats, then you'll need to know to remove that L2. You need to get rid of it when there's only one column of data. You need it there when it's two. So like I was telling you, it doesn't even give you the SX. It gives you the mean right there. So you can get the mean right here, and see it's giving you the standard deviation right here, 4.26. Now the same issue comes up here as it did before. You don't get variance from the calculator. It only gives you standard deviation. That's not a big deal. You have to just take in this number, and this I'll show you this in the calculator. I won't. I'll just use 4.26, maybe to be accurate. On a test, it wouldn't matter, but MyMathLab, you might want to give it a few more. Well, I guess since I'm looking right at it, I'll put a few more decimals in there. I'll go. Sometimes I'm just paranoid about what the MyMathLab's going to want. That's good, 676, and I'll square it, which is right there. So there's your 18.12. So that's not a big deal. I don't think that's a big problem to do that, to take that number and square it. But let me show you what you got to do in Excel. I'm going to tell you, I personally have a preference for the calculator on this one. But once again, I've mentioned many times before, it's you can use whatever you want, whichever way you want to do it. But I think that's, and I've also mentioned the beauty of this is the flexibility of you can change. Oh, I like calculator for this one. Oh, I like Excel for this one, other thing. So you don't have to stick to one. But there is no command like there is in the TI calculator. I had to create a formula. So here's the X, here's the PX. And this third column is X times PX, which you can see A2, A2, A3, they're all multiplied. And then I use the sum command to add those up, which I'll do it in a real live example here in a minute, but I probably summed it by dragging the columns and hitting that summation key, like that. You can either type in the formula like that or use that zigzag thing right there. And I got the mean, 8.4. So you see I used the mean right here just to reference this cell right here. Now this column, I went ahead, I didn't create a separate x squared column. I just squared it right here in the formula. I created the x squared px. So you see over here, I'm squaring it right here in the formula, a2 squared times b2. So there's x squared times p. X squared times p, so forth. I added those up. Now the variance will be the sum of these, which you see I have right here is D7 minus the square of the mean, which is right here above it in C7. So it's D7 minus C7 squared. And standard deviation, I just did, square root of, oh, looks like I did it from over here. I could have done it right there. Well, I guess it's the same cell, same thing, yeah. It's a square root of that number, and there's 4.2567. Now, the one disadvantage of this, is you're going to have to change your formula up a little bit. I guess you could probably, if you, let's say you're going to do one with more data, actually, I guess you probably could just insert some rows, and I think the formula would adjust itself correctly. Yeah, you could do that. You just insert some rows, and that should probably be okay without having to. You may have to drag the formula down or something. I don't know. But anyway, there's not a real nice way specifically to do it in Excel. It does involve using the formula. So here's another one. Did I do this one? I didn't even do this one in Excel. I guess I could. Here it looks like I used the formula, which not required. So here's the distribution. So I could probably get rid of that, but now I've told you verbally, don't worry about it. So sigma squared was xp, 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 xp minus the square of the mean, which is 2.5. Okay, using the other formula, forget that. Don't worry about that either. Okay, here's one var stats. I'll put this one in here. All right. I want to be able to see everything. One var stats. L1. Oh wait, I'm sorry. Got to enter the data first. Excuse me. Stat. Edit to get the list in there. So it's okay. Get that junk out of my way. So I'm going to go up here. I'm going to clear the list. Clear, arrow down. 1, 2, 3, 4. And then 0.1. 0.5. 0.2. Enter. 0.2, then enter. 0.2, then enter. So I can quit out of that. Go stat, calc, one var stats. Now I got to go second 2 right there, brings up L2, so I got to have the L2 in there. And then you can see everything here's right there. I can't decide if I want to wait to the homework here and just show you the Excel. Yeah, I think I mean, you can try this one yourself if you want to, but I'll just wait till we get to the homework and I'll show you a couple in Excel there. So, anyway, we know we're going to be able to check our answers there. So, all right, let's move on to the homework. 4.1. Wait, that's not what I meant to do. Not edit, I want to preview. Okay, I kind of skipped some of these and just get to the... All right. Okay, well, this one's interesting. Oh, wait, I'll go back to that one. Oh, either one of these, actually. Let me see what all the questions are asking. Oh, well, it's got a little graph with it. Let's see. That's a good one. Let's see what this one is. Same thing. So, more numbers, I guess. Okay. But you see, these are frequency numbers. So what we'll have to do is we'll have to convert them to probabilities by dividing by what the total is. Now, whether I use Excel or the calculator, I still want to. All right. So what I'm going to do here is I'll just, I can put something there. Your X's are in the first column. Actually, I'm going to do this. I'll show you why in a minute. I'm going to take, well, let me, sometimes the problem will tell you the total, but we don't need the total. We can drag it down and hit that sum key and that'll tell us the total. So I'm going to put equals the C2. I'm converting these to probabilities. Divided by, I'm going to put the dollar signs here because I want this to stay fixed at C9. Because that way when I drag the formula, it'll change it, the numerator, to C2, C3, C4, C5. But those dollar signs, that means it'll still divide by that same number. And I'm just going to, this is optional right here. But you can, if you don't want to, I saw that it said 3. Check whatever the My Math Lab wants. But this way, if you don't feel like thinking too hard, you can just, format, number, That way it'll already be there in 3. We'll see it. All right. So it doesn't really matter what I do it this way first, or I'll do calculator first. That's fine. And then I'll come back and show you the Excel. So calculator, I'll go stat, edit, list. And since I know that I'm typing in more numbers than are there on the screen, I can just type over it. When it's fewer numbers, you got to clear the list, because then there'll be numbers at the bottom you don't want. But if you just want to clear the list out of habit every time, there's nothing wrong with that. 0, 1, 2, 3, 4, 5, 6. .167. .089. So hopefully I did that correctly. So I'll second quit, and I'll go stat, calc, 1 var stats. So you see my L2 is still there. That's what I'm talking about. You just have to, if you've been doing this, and I'm saying if you go back though and need to do something else, that's just one variable data, then you'll have to get rid of that L2. But it'll stay there, I believe, until you change it. Okay, second quit, dimensions mismatch. All right, I did something wrong on the enter here. Okay, I had a number 1 typed up there on top, and I deleted it. And now let me just look that everything lines up. 6 goes across with .089, but that error was based dimension mismatch. I mean, you can't have different numbers of values in each column. So, which I'm glad it gives you that error message, so it doesn't give you the wrong calculation. Okay, I've already explained this. Okay, so there's what we need. Let's see what's asking us. Oh, we got to put these values in there. Oh, good grief. Okay. So all right, how can I get that to, I think there's a way to split screen this or something. I want that to stay there when I type in each number. There we go. Of course, I'll have to scroll over, but that's no problem. .167, .286, .224, .151, and .089. All right. Okay, let's see what's wrong here. Okay, I found the problem. Well, number 1, I wish I had a lighted keyboard. That would be helpful, but I had answers in there that had comma instead of period right here next to the keyboard, so that's why I didn't like it. The numbers themselves were right, but I had a wrong in front of it, so. Oh, this one's not asking for variance or standard deviation. Well, hopefully that'll be, we'll see that coming up here. I can find another one, I'm sure. Which histogram looks correct here? Well, you see the first one's pretty low, at 0, 2, 6. So it's got to be either B or C. Next one's 0, 5, 7, about halfway up. Okay, the first two are the same for B and C, but now we'll figure it out. 1, 6, 7. Yeah, see the 2 is too low for answer C. It's too low for answer C. That's about 1, 6, 7 right there, so this has to be it. I didn't realize this one wasn't going to have a... Oh, okay. All right, so that looks kind of symmetric. It's not clearly blatantly skewed, certainly not uniform. All right, well, now we got to get a... Okay, let me look at this before I start doing this. All right, that's a good one. Well, let me just look ahead. I want to make sure we get the variance and standard deviation. That's easy. Okay, this is a good one. I can go back to that other one. Or actually, that other one, I can just probably explain it verbally real quick just to show you, and then I think you'll be okay on that one. But I'm mainly interested in the ones that involve the technology here for now. All right, so let's clear this and get some new numbers here so we can. Because I'll put this one in both. So the last one, I basically entered it for nothing. Sorry about that. Because all we had to do is get the probabilities right here off the spreadsheet, and we had it. Well, I guess you got to see how to do it at least. But now I'm going to show you how to do it in Excel. So here, everything's all set up. So I'll do the calculator real quick. Stat, edit. Okay, now I got to clear both these lists because now I'm entering in fewer numbers. Zero, 1, 2, 3, 4, 5 on the left. So these are already probabilities. I won't have to convert anything. And I missed the 2. Um, 0.676. So now they're in there. I can go stat, calc. All right, 1 bar stats. So there we have it. Let's bring up. So the mean is 0.528. One decimal place? That's weird. That is really weird. Variance to 1 decimal place. Okay, once variance first, that's all right. See, there's the standard deviation right there, so we just have to go 944 squared. I'll remember the 944. It's going to get rid of this, and I type this. I used to leave it, the old calculators did. But we can see it, so 0.9. Well, this is really silly. I don't like this at all. I mean, 2 decimal places would have been fine. That was also going to be 0.9. Just because of the rounding. But you saw the process, how to do it then. So household has an average of 0.5 dogs, standard deviation of 0.9 dogs. Okay, well, all right. I like the question, I just didn't care for the rounding. Now let's, what were the next two? But I'm going to go back and, oh, here's an expected value problem. We probably want to look at that. I want to show you how to do this last one in Excel. Oh, the numbers are different, but we have the numbers. I can get them from, well, the data's still there. Now, I have this sort of set up. I didn't put the formula in there. Actually, I did do an x squared px. Oh, yeah, okay, so this one was 0, 1, 2, 3, 4, 5, but I didn't put the formulas in there. That's the only difference. Thought I had it set up, but I didn't. Just have it labeled. And the P's are, oh, I can get them from, oh, what am I doing? I can just copy them. What's the matter with me? Well, they're already there here. Now, I'm going to show you something when I copy these, because these, no, I'm sorry, it was the other problem. You know, the problem where, I'll just mention this one where we had to divide, you know, the frequencies and divide and copy the probabilities. And create the probabilities. If you were going to copy those over, you would want to do a paste thing here where you paste them as, or paste, but there's an option there that's for paste values, because you don't want to, because if they were created by a formula, you don't want to paste them as the formula. So it might give me, I'll do it right here just to show you, even though they were already values, but there it is right there, paste values. If they were created from a formula, that's what you definitely need to do. So now I need an equal A2, B2, A2 times B2 column. And I want to grab the corner and drag that formula all the way down. Now I'll grab the center, go all the way down right below it, hit the auto sum, and that, let's bold these. I'll reference that cell right here as, that's C8. There's your mean. Now the variance, I'm going to do equals x2 squared, so it's going to be equals A2 squared plus P, so it'd be B2 times B, not plus, times B2. Oh, it's not that. I'm going to grab the corner. Then I'll grab the middle and add those up. So the variance is going to be that 1.17, which you could just put in 1.17, but D8 minus the square of the number right above us here, G2, the mean squared. I could say C8, either one of them. I could say C8 or G2. It's in the same spot. I'll just go to, I'll go C8. Doesn't really matter. Squared on the C8. And standard deviation will equal square root of the number above it, G3. Alrighty. One decimal again? No, it's a different problem. No, I'm on a different problem, aren't I? Okay, I made a mistake. I forgot when we changed and I went back to that problem, it changed the number. So all I've done, everything, all the other work I showed you was fine. I don't have to redo all that. Is I just copied and pasted a new set of P's in there. And so everything, all the formulas were all set up, so everything's good. So these are the new P's, so these are the answers we want right here. So 0.51. Yeah, I don't know why they were doing this, bugging me, that one. I don't like that one decimal place. I guess because, oh, they're doing the half dog. Yeah, I was trying to do the last problem over, in Excel, but yeah, I was using the old numbers, and now we have new numbers. But I'm still showing it to you in Excel, so we're okay. We're not getting the same answers, of course. So the variance will be 0.8, standard deviation will be 0.9. All right, there we go. Okay, so, oh, there we go. So we're answering, but it's a different answer this time than it was before. 0.5 with a standard deviation of 0.9 dog. All right, now I'm going to go back and do one more before I end this video. The one that was the expected monetary value problem. That was easy. Unless it was ahead of me. Okay, maybe I went the wrong way. It might be number 11 or 12 or 11. Let's see. Yeah. Here's a roulette question. So this is kind of giving you a special scenario here. So let's put this on a... Let's use a new note sheet here. I'll do my best here. Or actually, I could just put it in Excel and type it instead of trying to write it by hand. Doesn't really matter where I put it. I could put it right back in this formula. But anyway, let's look at the scenario. Where did it go? Oh, there it is. Player bets $7 on a number and wins, and the player keeps the 7 and receives an additional $245. So I'll just, I may copy and paste the number somewhere, but I'm just going to put this over here. Let me just copy these two. So that means this will be a plus 245. I'll just put, I won't put a plus sign there. Now then, let's see what that scenario said. It was picking one number, I believe, out of 38. Bets on a number and wins. So if you're betting one number, that is 1 out of 38 probability. I think I have to put it equal there, I believe. Or it might think it's a label and not a value. And let's see what else is going on in this problem. Otherwise, you get nothing. And they take, okay, all right, so, yeah, this is just like, it's not just like, but it's an idea where, as an example I did in the notes, you're either going to win, well, this time you're going to win $245 or you're going to lose $7. It's just you have a higher likelihood of losing here than you did if you're just betting on red and black. So let's come back over here, and minus 7 is that loss, and then this probability would equal, yeah, if you're betting on one number out of 38, you got one winner and you got 37 losers. So there's your distribution right there. So I could do this in the calculator real quick. I can use that Excel sheet and do it, but you have to add it because when the number of cells are different, it might be a little more pain in the rear to do it. This might seem a little more efficient. I don't want to sound biased. I mean, it doesn't matter to me, but, and -7. Now in the calculator, I won't type in that decimal number. I'll just put 1/38 and it'll handle it. I don't need an equal or anything in front of it for the calculator. And then 37/38 here. So I got that. I can quit out of that. Stat, calc, 1var stats. So negative 0.368. Let's see. Nearest cent. So negative 0.368, well then would be negative, I don't have to, I'll put the 0 even though I don't have to, but 37, you round that 37 cents on average we should lose. There we go. Oh, that was it. Okay. It didn't want anything more than that, so that takes care of that problem. And I believe I'll end this video on probability distributions right here.